Mm, This one, oops. Okay, so good, great. So good morning, everyone. We had very nice talks today. So basically, today I would like to quickly, hopefully in 10 minutes, to talk about the role of embodiment and interactive visual-tactile perception and learning, especially with the focus on robotic grasp and manipulation. So basically what we are working on here in our labs have two sides, because I have two heads. One, I'm basically heading the BMW AI robotic research, and in the other hand, I'm also having a faculty position at Eindhoven University of Technologies. So we try to bring basically our research in a level of maturity which we can use it in industry. So here, yeah. From my side, when we are talking about, in general, very abstract cognitive systems or intelligence systems, I'm looking at multimodal perception or multimodal active sensation, and especially interactive perception, especially when it comes to some other modalities like a tactile sensing, which we had some the introduction today as well. And later on, we are focusing on the efficient learning, because when we are talking about the computational power, we can see the conventional learning methods like a deep learning and generative, I don't know, the AI, which is kind of a hype these days, requires too many resources. And in a learning part, we are trying to find out what are the efficient learning which we as a human we are using during the interaction, and to use less computation when it comes to the robotic as well. And then the last part will be the reasoning and planning. So a multimodal sensation for us is very important. And the idea, for example, in this area comes from the study we had when I was doing a PhD in University of Tokyo with Professor Yasu Kuniyoshi. And we collected the data from the human fetus. And this is a kind of a realistic simulation to find what is the first senses in a human. As you can see, the fetus cannot see and cannot hear it. And the only sense at the moment is more active is a proprioceptive information and cutaneous. And based on this movement, even the study says the first folds in a brain it gets develops. Based on this study, we moved to developmental robotics, which we have we have a first baby robot in the world, which has been developed basically in University of Tokyo. And I had a contribution there, and the robot can see and can basically hear. The voice has been made by the toy, but doesn't have a sense of touch here, if you see. So the first sense in human is the first sense of touch, because it doesn't let us to do just grasp and manipulation, but also body perception, self-awareness, and the other application. And this one was the motivation to develop the first whole body sensors. This is the robot. The first robot in the world had 5,000 tactile sensors, and we had to deal with many issues and complexity, from developing the stretchable, cuttable, the sensors here, and to find even how to compute 5,000 tactile sensors and how to use it and how to get the feedback during the whole body basically exploration. So the lesson we learned, the tactile sensing plays important role in our daily life, from grasping an object, manipulating them, realizing their physical properties, whole body perception and contact, to this social interaction and even self-awareness. So when it comes to the industry, you can see in industry we have many robots, but however, still people are working in the industry. For example, when it comes to the strawberry picking, the robot cannot feel the strawberry, can easily smash the strawberry. Why? Because the sense of touch is missing here. And the idea was how we can bring it basically to the robotics. And again, when it comes to the industry, we can see, although we have a robot can see very well, but they are kept in the cage. So how we can bring the robot outside the cage and keep it to the human, this is very challenging. Of course, we are moving to the soft body, but we have many robots at the moment, they have a rigid body. How we can make safe and intuitive interaction? For example, here we have the robots, there is no vision, and the robot easily can crush the objects. But having a sense of touch, the robot, of course, can easily even grasp the transparent objects, while changing the weight. Of course, we need some methodology and algorithm here, which, for example, we developed for the robots. The robot can do most challenging task, which is grasping deformable object, which is transparent and has dynamic center of mass, means the robot can basically manipulate them. Let me go a little bit faster. You can see this is the most difficult task, which blindly robot can do here. And this led us to go to the next slide, which the sense of touch is not basically crucial for the grasp and manipulation, but also whole body. This is during my PhD. Basically, this is a UR5 robot, and we covered the robot with tactile sensing. And if you can see, even we will be able to touch the robot, to move the robot, even to teach the robot how to perform a task. Even we can basically make the robot will be compliant, and let's call it like a safe as well. And we can move even with the feather. And if you will get closer to the robot, definitely will not kill you or basically smash you here. However, there are many challenges, and the most important thing when it comes to the tactile sensing, the tactile will be in contact with the human and object, and you cannot collect too many data, right? For example, with the vision, you can millions of data can be collected, but with the tactile, if you touch the object which is rough, or basically has let's put it in the way, is very rough, then the tactile sensor will be destroyed like a human. If you touch your hand over the rough object, your hand or your skin start bleeding. So we need to develop new methodology and algorithms which requires less training. So this is basically overall challenges we have. When in human body, we have 5 million, right? How we can deal with basically the computational part, in processing, and how we can bring a new methodology and algorithms, and how we can get a benefit during the interaction. So therefore, we started working on not only the tactile, because in the real life, we are using a multimodal sensation. In this case, we brought both vision and tactile via the interaction and active learning. So meaning that if we reduce the complexity, because when it comes to, at the moment, object handling, and realizing the simple properties of the objects, meaning that visual, like a shape, which can be via the vision, and the other properties which vision cannot give it to us, like inertia, stiffness, texture property, and so on. How we can get benefit of both vision tactile during the interaction, efficient interactions, by reducing the complexity of the hardware. So do we need really complex robotic hand in order to recognize the properties of the object? Or if you see here, even the smile kids with one finger and pushing the objects will get to know about the object for later on proper and dexterous manipulation. These are the works basically we have done, has been done with my PhD student Prajwal, and how we can bring both vision and tactile. And there will be another thing here for the first time we introduced, how two robots with two different embodiments can share their perception and to work together in order, for example, here to declutter the scenes, even if the objects are transparent, which is very difficult, to reconstruct the shape of the objects and to robustly detect the pose of the object here. So we don't have time. I will just show you here how the robot is actively, there is no human in the loop, is actively looking at the scenes. And the other one basically is trying to touch in order to reconstruct the part didn't be able to see by the other robots, in order to have a full basically shape reconstruction here. And basically this would help the robot here to estimate the shape and to also to calculate the pose of the objects, even is a transparent for the dexterous manipulation. And the other thing basically is here, the object cannot be only in the hand, object can be big, you know, and the other thing is the object can be soft or will be articulated objects. These are very challenging, and how both robots will be able, by simple and action, using both both vision and tactile, to estimate the properties of the objects basically here. This is basically the proposed method we had, and we are using a DDF, which is a dual filtering approach, differential dual filtering approach, and we published recently in a TRO, and we showed that simple action can help the robot to estimate the properties of the articulated object toward manipulating the soft object. And the last thing basically is I would like to basically present it here. For the first time, like 3-4 years ago, we proposed the cross-modality in the robotics, meaning that when it comes to the human, when we have a vision and tactile and some motor-sensory, and there is an overlap between these areas. And while we are learning, for example, about the one objects, all sensing modality will work at the same times. And later on, when we are only looking at the objects, right, and the visual perception will help us to have prior knowledge or kind of an estimate about the other modalities, which we call it, for example, tactile. In this case, we used visual perception, and the vision will give you just the understanding about the shape of the objects. This is the active, we call it the active visual perception. And later on, this active visual perception will help the robot when consider, for example, if the room is dark or vision is completely off, the robot will touch in order to recognize the object. What does it mean in real life? Consider you have your mobile phone and you know the shape, and when it's dark and you want to find the your mobile phone, you are just coming and touching, and by touching basically the surface of your iPhone, which is smooth, you realize, okay, this is my my iPhone, and you can estimate also the shape already. But the complexity basically in robotic comes how to bring these two different sensing modalities or distribution in one, which we call it domain adaptation, or basically domain transfer here. And here you will see when Prajwal is hiding, or let's say the covering the cameras here, and the other robot with other embodiment and sensing will be able to estimate the shape and to recognize the objects for grasp and manipulation. And this is basically has been evolved more, which we are now going to publish to the Nature. This is the cross modalities, has been done by my PhD student, Anirwan. He will submit the thesis this month. And the idea is, again, by looking at the apple, we will be able to have the prior estimate or prior knowledge about other modalities, means smoothness, which we don't have any experience, or vice versa. If you see the object is, for example, smooth or is rough, then you can estimate the shape of the object, or, for example, the textural properties of the object we have. And this is basically some of the initial results we have. And the robot, by looking at the objects, will be able to estimate, to improve the estimation of the weight, center of mass, and so on. So this is kind of a new approach to the robotics. This brings a robustness and brings also the ability to the robot to use much less data, and whatever will be learned will be transferred to the other, different embodiment, which we call the cross embodiment. By this slide, I would like to finish. I think I'm over 5 minutes over. I'm sorry for that. And I would like to thank all my team. And I'm happy to take any question if there is a question here as well.
Thank you very much.